Good morning, good afternoon, good evening, everyone. Welcome back to Apaya Puzzles, and I'm very excited to be tackling yet another of Marty Sears puzzles. This the sixth in the series of the Rat Run series, Rat Run 6 Equilibrium. Now, I published a few days ago Rat Run 4, which was a great solve. I hasten to add that I think it was this morning actually, Cracking the Cryptic did that same puzzle. And Simon very much put me to shame in terms of my solving skills. I think he solved it in about half the time as me, and with, as he would call it, a great deal more alacrity than me. But I can aspire to improve, and the only way to do that is to keep solving. And I have done number 5 as well. I did record that for the channel. I'm debating whether to put it up because it was a brilliant puzzle, and I solved it well, but there were a couple of assumptions that I made which happened to be correct, but which weren't strictly speaking logically proven by me. So I'm debating whether to do that, maybe cut in a few times to explain a few things. But whatever the case, I will be doing number 6 today. And I saw this on Logic Masters an hour or so ago over coffee, and I read the rules and actually had to then immediately look away because it was one of these puzzles where there's a rule, the key rule involved here, that is quite unusual and gets, if you keep staring at the grid, you can't help but start thinking about what the implications of this rule would be. And I didn't want to preempt that process. I want to try to capture it in all of its glory for camera. So we'll see how I go. I'll put a link to this in the description if you want to give it a try. Marty has rated this 3 out of 5 for difficulty. Hasn't been solved enough times yet to get a community rating. The puzzles in this series have all been 3 or less for difficulty, and all exceptionally well received in terms of satisfaction ratings. I won't wax too much about Marty. I did in my previous video. He's a brilliant setter, and this is just one series of many kind of very creative puzzles that he's created over the last year or so. But without further ado, this rule set looks intimidating, but it's not too complicated. It's just quite a few rules. So let us read them and then proceed. So let me just find everything. Okay. So, and just a quick appeal to anyone who would like to subscribe to the channel. I'm on my way towards 100 still, so hoping to get there soon. So by all means. Now, Rat Run 6 Equilibrium by Marty Sears. Normal Sudoku rules apply, which is to say that every row, every column, and every 3x3 box, oh good grief, my mouse is really not my friend today, contain the digits 1 to 9. Frustratingly, the software I use for recording this on my Mac tends to cause lag in the system, which makes this mousing around a little bit tricky sometimes. Which mousing around being appropriate because we are indeed following the journey of Finks the rat today. The aim of the experiment. Finks the rat must reach the cupcake by finding a path through the maze. The path must not visit any cell more than once, cross itself, or pass through any thick maze walls. So Finks here is going to travel through the maze in these kinds of movements. Let's use the line. Oh, I don't have my line tool. Hang on, let me grab the line tool so I can do that. Or the pen tool, yeah. So Finks is going to make some sort of path like this, moving left and right, up and down, but also, as it mentioned this yet, it will do in a second, can move diagonally if there's space for it. So it could do something like that. But she can't move across the corner of a line of a wall like this, and indeed obviously can't go through a wall, and she can't go back around on herself, so she couldn't do something like that and intercept herself. I think that's about to be explained. Well, yeah, that's explained, and then as well as moving orthogonally, Finks may move diagonally, which is in these 2x2 areas where it's possible. Now, teleports. This is a curious rule. Entering a yellow teleport in these corners will cause Finks to instantly be transported to the other teleport. From there, she can continue her journey. The teleport contains the same digit. So I take that to mean that if Finks came down here and entered the yellow, she would then emerge over here and exit the yellow. And they have the same number in them. One-way doors, we have these little inequality signs where one is bigger than the other, just like a normal greater than, equal than, greater than or less than sign. This number will be more than this one, but in addition to that, Finks may only pass directly through one of these purple arrows if moving in the direction the arrow is pointing. So if Finks is coming down this way, she can come through here because it's the direction of the arrow, but if she was coming up this way, she couldn't go back through there. Black currants, these are normally called crop key dots, but in this puzzle, black currants, cells connected by a black currant are in a 1:2 ratio. Not all possible black currants have been given, and that's just a fancy way of saying that one of the digits is 2 times the other. So if you had a 3 in here, you would have to have a 6. If you had a 2, you might have a 1, or you might have a 4. As long as there's this kind of 2 times one of them is the other one, then you're good to go. And just bear with me while I cough. And then finally, I've lost my rules now. Hold on. The test constraint, and this is where the rubber hits the road, although it's a bit curious this. In this experiment, the sum of the digits on the path before teleporting must equal the sum of the digits on the path after teleporting. And it's when I read this rule that I had to look away, because I thought, if I look at this grid, I'm going to start contemplating that. And it's a slightly hard rule to believe is going to be enough to solve the puzzle. And to explain, in these puzzles, all 6 of them, there's this idea of the rat moving through along a path. And the path normally has some sort of rule that stipulates the relationship between one cell and the next. For example, this one must be at least 5 away from this one all the way along the line. Or, you know, the cells on the line in this box must be the same sum as the line in this box, these kinds of things. These are kind of extensions of standard Sudoku rules, or standard variant Sudoku rules. But in this case, we have this rule that the path, all we know about it is that that before teleporting, the digits that she has traversed must sum to the same as after. So let's say she came around here, she found her way up to the teleport here, and then came out the other side and did another thing and another route and eventually got to this. All we know is that the sum of the digits on each side of that are the same. We don't know anything about from cell to cell what the difference is or anything like that. So actually determining what numbers are on the lines, there's no guidance to that really, apart from the other rules like these black crop dots and the greater than signs. So it's curious, although just as I did that example there, I noticed something interesting that might be relevant. So without further ado, before I start solving it in my head, let's go. Now, what I noticed, well, first of all, let's just make the obvious point that Finks has to get out from where she is, and there's only one way she can go at the moment. So she's going to go to there, and then it's possible that she goes either way here. And over here, she's going to come down. We don't know if she's coming into that or out of it, but whatever the case, she will be traveling through it. Actually, I should just kind of consider. Yeah, it's funny, it doesn't actually stipulate that she has to go through the teleports, but I find it hard to believe that they're not being used. So let's just assume for now that they are. I think it'll become clear. Actually, it is clear because this area over here, to get to this cupcake, either she comes through here or she comes through here, but she's not allowed to come through this one because it's the wrong direction. Let me just correct that line tool. Yeah. So she definitely will use the teleports. Now, what I noticed when I was explaining this to you and saying, well, how on earth are we going to get any traction just knowing that the two sums are the same? I realized that actually this area is quite closed. So, like, she's going to come through here. Maybe she comes in a little loop here, but when she to get to the cupcake, she can't come out through here because then she can't get back. So there's only a very limited number of cells that she could potentially use to get to the cupcake. So it's quite a small number. And that contrasts with a lot of cells that are going to have to be visited to get up to here. So we're probably going to be looking at some sort of minimum maximum thing where like the highest possible sum she could reach over here is going to be the lowest possible sum that she could reach over here. And I can see how that could be useful. So yeah, I mean, I think that's probably worth considering because I don't see, yeah, interesting. But the thing, see if this is the lowest possible, then it's not going to be taking in any of this part of the grid because it's going to have to be some sort of direct route. And that seems surprising. It feels like there's going to be some need to go up here, particularly because we've got these areas where she can go diagonally. And normally if there's areas like that, they'll probably come in handy. They're not necessarily going to be used, but at least one of these diagonal things will be used because there's a rule stipulating that possibility. Well, let me just, I think I should pursue that thought for a second. I don't think there's much else I can really do. So let's see, let's say she visited every one of these cells. So she came up through here and then she came around in a loop and then eventually down to here. And we could ask ourselves, what would the sum of that line be? And we don't know exactly, but we know something about it. So because she would have visited every cell in this box, and we know that every box contains the digits 1 to 9, the infamous secret is that the digits 1 to 9 sum to 45. That is an immutable fact of the universe, and so every box in a Sudoku does sum to 45. So these cells would make up 45, and then there'd be these additional cells that we have to add into that. And I reckon we're going to look at what the maximum possible sum would be in this instance. So 45 here, and if these were the highest numbers in the box, which is to say 5, 6, 7, 8, 9, that's going to give us the maximum possible sum for all of this if she was following this path. So 9, 8, 7, 6, and 5 sum to 35, plus the 45, and that gives us 80. So let's just highlight that so we can remember what we're talking about. Those cells have a maximum value of 80, and so if she traversed them, she gets that much. And so we've got to keep her down to no more than 80 coming this way, because otherwise, if this sum over here is 90, there's no way for her to achieve that. And that seems tricky because she's got to go a long way, so there's going to be a lot of cells that she's taking in. And you know, in simple terms, we could just make the basic observation that, for example, it's not possible for her to visit every cell in both of these. There may not be a specific route that does that, but even if there were, you couldn't, because that would be 2 lots of 45, that's 90, and that's already too much. And as you can see, we still, from here, have to get a long way. So I want to speculate about a shortest possible route, which is going to be, oh, well, she can't come through there. That's interesting. So actually, she has to take a circuitous route in the first instance to get out of that box 1. And then let's say she went, we're trying to go as directly as possible. The particular direction is a bit hard to, we can't stipulate exactly what I'm trying to say here. When I'm doing the minimum route, what I'm saying is like the least number of cells she could travel, but I wouldn't know specifically which one. So she has to take the most efficient way. So this would be efficient, but this would also be efficient. What we're saying is basically that at no point along this route will she go backwards when she could have gone forwards towards the goal. But that route doesn't have to be along there. You know, it could be just as well be this. But the main idea is to know how many cells she's going to be taking in. So if she takes the minimum possible route, remembering that she can travel diagonally here to reduce her steps a little bit. And again, it could may not be this diagonal, but it would be one of these to shorten the root. Then here, then here, then here, oops, then here, and then the last digits. Now, I mean, that's a lot of cells, and somehow they've got to be no more than 90. So let's do minimums. So if this was 1, 2, 3, 4, and 5, that's 15. If, what's the best way of doing this? If this was 1, 2, 3, 4, and 5, that's another 15, that's 30. We've got 1, 2, 3, and 4 potentially, that's 40. 1, 2, 3, 4, and 5, that's 55. 10 in here, 1, 2, 3, and 4, that's 65. Plus 6 in here, 71. So there is some scope there. Which is a bit surprising. It's quite a lot of leeway. 19 degrees of no, hang on, it wasn't 90 over here, was it? It was 80. Did I just say 70, 71? I think it was. So there's maybe 9 degrees of freedom, something like that. Still quite a bit. Yeah, it's still going to be that most of the cells she takes have to be low, and she can't go that far out of her way. Like, for example, if instead of coming through here, let's say we got rid of this, and she came around like this, we're adding 4 extra cells. We had 1 here, but now we've got 5, so there's 4 extra cells. And the minimum that 4 cells can add to is 10, 1, 2, 3, and 4. And that would already break the situation. So actually, she can travel diagonally there though. So she could do that, which is adding only 3 cells to the path, which would just work. That's annoying. Because I was going to say we can eliminate the possibility of her coming around here, but I don't think that's true. Are there other possibilities that we could eliminate? Well, okay, what about here? Instead of going that way, could she have gone 1, 2, 3, 4? That's adding 3 cells as well. Which again is theoretically possible. But if you did do that, then you can't do the same at the top. So well, one thing I think we can say is that she's not coming through here, because she'd have to take those 4 instead of those 2, so that's added 2 cells to the root. Then she'd have to add another 2 cells. That's, oh no, that's okay. 4, oh what, maybe. No, it feels a bit awkward. So 1, 2, 3, 4, 5, 6, 7, 8. That's 9 cells. Whereas this way, coming from here, she could have gone 1, 2, 3 cells, or 4 cells to get to the same point. So it's 4 cells to get to here versus 9 cells to get to here. That's five cells, which, but those 5 cells, I was going to say they have a minimum of 1, 2, 3, 4, 5, but that's not true because they could repeat because they're not in the same box. So it still seems unlikely. And this is the point where definitely Simon's doing this more efficiently than me. Well, we do know that she's not coming over here, but that's not helpful to us because, well, I say we do know, I'm pretty sure we know that. But in any case, it wouldn't really help to know that, I don't think. If we knew that she definitely did come this way, then it would help because it would be forcing this total to be much higher and probably couldn't get any higher without breaking this. And so we'd have a forced sequence. But we don't have that. Now then. Oh, actually, she can't come through there anyway because, oh no, so she's coming this way. So she could come through there. Oh, hang on. Whoa, whoa, whoa. I keep making this mistake. I made this in Rat Run 5. This is part of the problem why I didn't publish it. Is I forget which direction she's coming from. So she can come through there because she's coming from over here. But this one, she actually can't come through there because she's not coming this way. She'd be coming up through this to get to this. Oh, that's huge. So this is really important because now let's imagine a slightly different route here because we're trying to do the most efficient route. Is coming across here, but then not being able to go up through here. So she comes down, across, up, potentially diagonally to cut some cells off the path. I don't know if this is going to make it better or worse or no different. Up here, to minimize the path, we go diagonally because that's one step rather than two steps. Then across and then up. So that is one efficient route that she can take. And now we can do that similar calculation that in this box we've got a minimum of 1, 2, 3, 4, and 5 for 15. I don't think there's anything obstructing that from happening. 1, 2, 3, 4 for 25. 5 in here makes it 40, 50, 60, 70, and 80. There we go. So that is exactly 80. So the minimum possible sum of the root on this side is 80. And the maximum possible on this side is also 80. So there's no room to move. They have to be exactly that. The specifics of this path over here may be different because there are different ways of taking that efficient route. So for example, here she could have come across rather than coming down, and it's no different. But the diagonals will have to be taken. I don't think there's an alternative way of, no, you can't. So you're going to have to do that diagonal. Let's maybe mark these in a color. This diagonal, no, that doesn't have to be taken because you could have come to here and then taken that diagonal instead. So that's not clear, but one of those diagonals has to be taken. And we took one here, and there's no getting around that. And we took one in here, but that could be that one, or it could be that one. So that's not clear. Now, but what we know now is that this is actually 80 in total. So 45 here, plus the 35 here was where this was the minimum possible, 1, 2, 3, and 4. And in fact, well, moreover, actually this set here, there's no, you can't do anything but this, because if you came down, you're losing efficiency. Oh, no, you're not, because you come, no, you are, because 1, 2, 3, you can go diagonally 4, 5, 6, but that's 6 cells rather than 5. So this is definitely the root here. They have to be minimummed to ensure we get exactly that 80 and not any more. So they are 1, 2, 3, 4, 5. And Finksy is going to do this, 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 and she has to come down because if she came across, she wouldn't be able to make use of the diagonals in an efficient way. So if she came this way, she's automatically using an extra cell. That's 5 cells rather than the 4 that we're trying to travel. So she must come down, but we don't know if she takes the diagonal here or here, but that's okay. We do know that she's coming to this cell and to this one and to this one, and this box has to be the minimum they can. So these are from 1, 2, 3, 4, and then it's a question of whether she comes to this one. Maybe I'll try to highlight, maybe it would have been better to highlight I'm just going to highlight this in green. Does that look good? Yeah, and so one of those two is used, but I don't know which one. And it will be a 1, 2, 3, or 4. These are definitely, in fact, they're all definitely used. There's no alternative. So we'll call them, yeah, I might just get rid of the orange where I can and say blue is the definite. Well, I can just use my line tool, so maybe getting a bit confused between colors and lines here. Actually, that might be a better thing, is just to get rid of the color once I know the line, and then leave open these kind of ambiguous ones. So one of those two, that one's definitely on the line, and so we can give it the line. This has to definitely come out from here, so we can get rid of the colors here and here. We also know that these are the minimums that they can be, 1, 2, 3, 4, and 5. This is from 1, 2, 3, and 4. There'll be 4 cells in this box that are used, and that one is definitely one of them. So we're going to make these ambiguous, but we're definitely coming to this cell and down. We're definitely going to come through here, 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 and here. So yeah, that's all very forced. So I'll get rid of these colors, and then we can sort out a few of the implications of this. Yeah, definitely. And so then there's this question about whether it comes to here or directly to here. So these two here, the ambiguous ones, this is definitely in. And I think we're good. Now, I may as well get rid of this purple as well. That's not of any use anymore. Now, a few things. We have these crop key dots, or these blackberries as it were. So they can't have a 5 on them, because 5 doubled is 10 and halved is 2.5, so that's no good. And they can't have a 3, because 3 would have to go with a 6, and we know there's no 6. So this is either a 1, 2 or a 2, 4. Always has a 2 on it, so we can get the 2 out of, oops, get the 2 out of both of these. There we go. So this lag is quite frustrating. This is also a black dot, so it can't be a 5. It could be a 3 now, because in fact it probably is a 3. Maybe not. It can't be a 1 because it would need a 2, and there's already a 2 here. So either it's a 3 going to a 6, or it's a 4 going to an 8. It can't go to a 2 again for this reason. So we get that. Now, so this is also a crop key dot, but that has quite a few options because we don't really know if it's going that direction or not. We've got this over here as well. So we know that all these are 1, 2, 3, and 4. So again, this has to be either a 1, 2 or a 2, 4 with a definite 2. So that's not a 2. This same deal. So this can't be a 1 or a 2 because the 1 would need a 2 here and a 2 is already taken. So the 3 either goes to a 6, or goes to a 6, or the 4 goes to an 8. So that's the only way that can work. Still does seem quite surprising that this can be solved uniquely, having basically solved the path. So 6, 7, 8, 9. What about the crop key dots over here? Well, can't say a great deal about that. We've got 2 of them there. And we know that she has to take every cell over here, so she's definitely doing this. And then the only way to take every cell is to come this way. So that is the path to the cupcake. But as I say, like knowing that that's the line doesn't really do anything, because all we know is that it sums to 80, which we know anyway now. So the actual order of the digits is not specified by the existence of the line, which is unusual for a line puzzle. Now then, what do I do? Well, the cells that are in here have to be minimized. So they're 1, 2, 3, 4, and 5. This is on a black dot, so it's not a 5. I should also just be mindful of looking for example, we've got a quintuple there, 1, 2, 3, 4, and 5 in the column, so the rest of the column can't have any of those digits. So that makes these ones 6, 7, 8, and 9. And then these greater than signs can help, so that can't be a 6, and that can't be a 9. And down here, this is less than the one next to it, so it's not a 9. So there we go. We just from doing that, the 9 can't go there, and the 9 can't go there. So the only place for the 9 that is there. Also in that quintuple, 1, 2, 3, 4, and 5, the 2 can only go up here. So by there being a 2 here, there's not a 2 here. And also, we've got 2's there, but also 2's here. So this here can't be a 2. So that is a 2. And we've got a couple of digits in the grid. Let me turn off the red pencil marking that highlights. It's a bit of a shortcut to solving the Sudoku side of things. Well, I've got the notes, but where was I? I was thinking about that column, but before that I was thinking about this, wasn't I? So this either is one of the small digits and the line is coming this way, or it's a bigger digit like a 6 or an 8, and then the line's coming directly to there. 1, 2, 3, 4. Yeah, well, on the big and small idea again, we know that those two have to be big because, or big-ish, because the 1 to 5 is used up here and 1 to 4 is definitely used down here. So these have to be smallish. This can't be a 5 or a 9, and it's more than this one. So this one can't be a 9 or an 8 now. So we have a similar, well, not quite. I was going to say we know more about the 9, but the 9 could be in one of those, or it could be down here. Let's have a look at this 9 while we've got it. Yeah, okay, so the 9's not in anywhere there, so it must be there. So that is a small win. 9's through there, and it's not on the less than side of a greater than, which means it's not there either. So it must be there. And we know that this set here is the big set, 5, 6, 7, 8, 9. So the 9 has to go in there due to this 9, and then it goes in there. Here we go. This 9 here is not in there. It's not on the Kropke dot because it can't be divided by 2. So although we don't know exactly where it is, we know that it's in one of these 4 cells. And that means that in this row 7, the 9 is not in here, and it's not in here from what we've just done with this 9. So it must be in here, in this row, and so it's in one of those 2 cells, which may or may not be useful. This one's bigger than this one, so this has to be 7, 8, or 9. And then this is just any value. Oh no, that's oh yeah, that could be the 9. I thought we were going to get slightly further with the 9s, but that's not too bad. I might get rid of this here because it's kind of a bit over pencil marked. We got the result we needed over here. So we are left with a 6, 7, 8 triple in this box to complete the box, and then the rest of the row is small. That's almost interesting. In fact, we've got a 1, 2, and a 4 here. So this cell sees 1, 2, 4, 6, 7, 8, 9. So it has to be a 3 or it has to be a 3 or a 5. Now, and then this cell, yeah, okay. Yeah, okay, so in this box, it's going to come to 4 digits, which will be 1, 2, 3, and 4. And one of these is involved in that. And it's not a 1, 2, or a 4. So it will definitely come to a 3 in that pair and then go diagonally. So there's no 3 in here. It might have been visible some other way now that I think about it, but maybe not. And that's not a 3, so it's a 1 or a 4. Get that 1, 2, 4 with the 3. That's all well and good. Yeah. Quite sure what the best strategy is here. Am I supposed to be doing more Sudoku-ish considerations, or I say Sudoku? Yeah, so we've got 1, 2, 3, 5, and 7. In this column, we've got 2 of the digits from 1 to 5 here. We've got 1 of them in here. Well, potentially 2 actually, but at least 1 from the 1, 2, 3, 4 that we're going to do. And then at least 1 in here. So there's only 1 of the small digits left, being 1 to 5, that is. I feel like that should be telling me something, but I don't quite know what it is. There's probably something more straightforward from Sudoku. This is 1, 2, 3, 4. This cell here is on a crop key dot, and it's not a 1, 2, 3, or 4. So the only digits it can be are 6 and 8. So you can't put 5, 7, and 9 on a doubling dot. So this has to be 3 or 4. That is getting us close. Oh, that's perfect. Yeah, okay. So now if we highlight those cells, we have 4 of the digits 1, 2, 3, and 4, and 5 in those 4 cells. So if Finks came this way, what cells would she put in here? They have to be small. They have to be from 1, 2, 3, 4 to be minimized. But that would give us a 1, 2, 3, 4 quadruple there, and this cell here would have no value. So that means that we can clarify that Finks goes this way, which should hopefully be pretty useful. We can get rid of some of these colorings. And pop in the 1, 2, 3, 4. Again, this crop key dot now can't, we can't use a small digit on this side of it. So 1, 2, 3, and 4 are gone. So the digits that can go on it are a 6 or an 8, which give a 3 or a 4 there. Now we do have, no, we don't have 1, 2, 3, 4 quadruple. Over here we've got 1, 2, 3, 4, and 5. So the 5 of them is up here and is therefore not in here. And the rest of the column is 6, 7, 8, and 9. Which doesn't look all that useful just yet. Can I pull a similar trick? I don't think so. I think that could be a 1, 2, 3, 4 quadruple. And then go diagonally to there, or it can go diagonally to there. We've got 1, 2, 3. Only 1 more small digit, which is not in here. So it's in one of these. Oh, right, okay. So it's not that useful, but the fourth of the 1, 2, 3, and 4s will be in one of these in order to keep this to its minimum. And actually I said, I think I thought this was 1, 2, 3, 4, 5. But because it's actually a 4-cell thing, these have to be minimum. They can't be 5. It's 1, 2, 3, and 4. Oh, that's really important because now we have this 1, 2, 3, 4 quadruple. So we need 5, 6, 7, and 8 still. I'll pop them in. And there will be a 1, 2, 3, or 4 in here. That's the quota of all of those. And we're left with 5, 6, 7, 8, and 9s around the outside. That's not quite as conclusive as I would hope, though. we've got a 1, 2, 3, 4 quadruple across there now, which means that this has to be a 5. And that being a 5, well, doesn't really tell us very much, I don't think, which is a bit surprising. Although over here now, again, we've used the 1, 2, 3, 4. There's a lot of repetition of this same idea, which is a really nice setting. So what's on the Crockey dot? It's not 1, 2, 3, or 4, so it must be 6 or 8, because it can't be 5, 7, and 9. So this is 3 or 4, and now we have this 3, 4, 6, 8 quadruple, or 2 pairs of doubles, or pairs. We also have a 3, 4 across here. We have a 6, 8 across here. Yeah, so this leaves us 7 and 9 in the row. We use 3, 4, 6, and 8. And we know that these two are on, these have to be big in order for this to get to 80 and all up. And it's not 6, 8, or 9, so these are the last big digits, 5 and 7. And then this is 6, 8, 9 with a definite 9. So now we've only got 1 and 2 left in the column, so they go there. That almost gives us a quadruple across here. If this went to here, then it would be a quintuple. Goes down, there's no problem, so maybe that's not quite helpful yet. 3 and 4. Where are the 1 and 2 along here? Yeah, this, there'll be a kind of X-wing on 1s and 2s here. We know the 1s and 2s are in there, and we know the 1s and 2s are in there. So in this row 4, the only place 1s and 2s can go are in there. So that's 1, 2, 3, 4. So they get 5, 6, 7, 8, 9 to play. So this is 6, 7, 8, 9, which we could just see from the box. In fact, I think I didn't mention that earlier. And this is 6, 7, 8, 9, because it can't be a 5. So the 5 in this row is definitely in there. And well, we've only got, well, we've got a few options down here still. So yeah, 5, 6, and 8 with a 5. I wasn't seeing that 7, 9 there. Okay, so still don't know what's going on in terms of which of these cells are being taken. This is 6, 7, 8, or 9. Oh, this is a, oh no, I was going to say that's a 2, that forces this, but it actually doesn't. We can take the 2 out of there though, so it's a 1, 3, or 4. We've got this 1, 2, 3, 4 along here, so the rest of the row is 5, 6, 7, 8, and 9, but we kind of basically know that already. So what do we do? What would Simon do? What would Simon do? And what would Simon be missing? Probably Sudoku, which is also my failing, or one of my failings. This is where you feel like, why don't I just pause and then come back and say, spare you the suffering of watching me wonder. 1, 2, 3, 4. So there is a 1, 2, 3, or 4 in here. But we know that. We know that this is 5, 6, 7, 8, 9. Am I forgetting an equivalence or inequivalence? This is less than 9. This is less than this one. Still doesn't feel very helpful. And there's nothing extra I know based on the sums. I think the sums are basically understood now. That's not going to give me more information. I hope I'm right actually with this. I didn't overlook something or miscalculate something, because that would be a disaster. Although, mind you, if that is the case, then you're not watching this, so all is well. I feel like that can still be a 1-2 or a 2-4, and that would be fine with this. The alternative, and then it would come there, or it comes directly there. So either way, that seems. Well, if it did come directly there, then that's a 1, 2, 3, 4, and this would have to be a 6 or an 8 as per the logic we've done already. That would be a 6-8 pair. This would be a 7. This would be a 9. This would be a 5. Everything would unfold. Ah, no, maybe not. Ah, right. We have 1, 2, 3, 4 in here. Now, if this cell came to here, we would have to go that way, and this would be 3 of the digits from 1, 2, 3, 4, which would also be in this set. So let's say this was 1, 2, 3. We'd know that 1, 2, 3 would also be in here. So in row 7, where's the 1, 2, 3? Well, they'd have to all 3 of them be in there, which is not possible. So actually, that does conclude that this must come this way and then down to avoid that exact scenario. And I think that is actually the path I was just spelling out the possibilities for. I might just get rid of those purples. Don't know what they were doing. Still ambiguous here, but now we know this is on the path 1, 2, 3, 4. Can't be a 3, so we need to go with a 6. It does have a 2 on it, so it's either 1, 2 or 2, 4. No 2 there. There is definitely a 3 in there. Therefore, that's a 4. That's an 8. Here we go. Get rid of the 8s there and the 4 there and the 3. Is that the only place for a 2 in the column? It is. That's the only place for a 2. So there we go. That's a 2. That's a 2. We can get rid of these 2s. It's getting a bit frantic now. There's all sorts going on. I've got to try to keep a track of the things I'm discovering. Oh no, that wasn't the case they spelled out, I don't think. So we're left, I think, with some ambiguity over here. But let's continue with what we've discovered over here. There's surely lots to say about this. We've got a 5, 6, so that's an 8 and that's a 4. That's a 6 and that's a 3. Is it going to tumble? Is it going to tumble? That means that there's no 6 in there. This one, we've got a 1 and a 4 in the column. There's probably so many of these things now, so I'll just take them in the order that I notice them. The 3 means this has to be the 3 in the box. 1, there's a 4 here now, so that's a 1. That's not an 8. We've got 5, 6, 7 in the column. There's now no 1 in there, no 1 at all. This is a 4 and this is a 1. So yeah, I think we really are closing in here. No 4, no 1, and I think that's still open. No, that's a 2. I wonder if we might have a chance of a 3 in a corner. This is a 1 by Sudoku. It's just, when we say by Sudoku, we just mean by the normal rules of Sudoku. That was a 1 or a 2, but the 2 here eliminated it. Gosh, there's just so many places to look here. So this is a 3 and a 6, again by the 4 on the right-hand side here. This is not 6. 3, 3, there's a 3 in here, which probably we already knew. There's no 4, we've used the 4 in the box now. So, and that as well, so that's a 1, 2, 3 in the row. This is not small, and it's not 5, 6, or 8, so 7 or 9. And the Sudoku pressure is real. So where am I supposed to be looking? 1, 2, 3, 4, still seems too open to, there's got to be something more obvious. This is more than that, that's fine. Sixes, there's a 6 up here, not surprising. Oh, the 1 there means that's a 3-4 pair, so that's a 1, which takes the 1 out of there, making it a 2-4. Oh, we had the 1 there as well, so that would have shown that. The 2-4 there makes that a 3 and a 4. There's no 6 in here, so we have an 8-9 and a 5-7. The 8-9 points up at the 7-9 there, which solves that. And that's not an 8, so there's 7-9 in a row. There's an 8 in here, which checks out. It's actually kind of surprising. I can't quite understand how this is resolved with so little information to go on. It's quite cool. That's a 1 by the 4 at the bottom, and that's going to be useful. That's a 4. We still know we're going to a 3 here, but I don't think we know which one's which. There's no 4 in there. So we're still with 1, 3, 4, and 5, which I don't think is quite resolved. There's a 4 in one of those, but that's not that interesting. Oh no, actually that 4 means there's a 4 in one of those, then there's a 4 in one of these, but this 4 looks up, so that's a 4. In the end though, not that big a deduction. 5, 6, 7, 8. I don't want to over pencil mark. Let's be sane here. We need a 3 up here still, so this is 3, 5, or 6. And then again, there's a 3 definitely in there, and there's a 3 definitely in there. So in row 3, the only place for a 3 to go is in the middle here, which is there. And that finally resolves our colouring because we have to take that 3. So I think that's the entire path determined by some sort of miracle. This only has a 5 left to go in it. So this is a 5, 6. Sorry, I'll just do. It's not a 5, so it's a 3, 6. This is a 7 and an 8. The 5 gives us a 6 here and a 5 there. 6, 7, 8. And now it really feels like it should be almost over. But how does one complete? This is more than this, right? So this is an 8 or a 9, which I don't think is resolved actually. And this is 5, 7, 8, 9. Oh, in fact, no, I don't quite know that still. Let me just quickly scan the black dots to make sure that they've been used. And I think I'm not missing one, that is true. This is less than this. So this has to be an 8 or a 9, but it can't be a 9. So that is an 8, and that's a 7. That will no doubt do some important, terribly important things. Or maybe not. 1, 3, 5, and 6 here. So this has to be a 5 or 6. Because 1 and 3 are in the column, and we need 1, 3, 5, and 6 in the row. This is 5, 6, and 7, a definite 7. Moron. Well, not moron. I completely forgot that these have to have the same value. There we go. They're both 5s. Wow, that was really it's such a relief that actually I wasn't losing my mind. Well, I felt like I was losing my mind, but it was in the end just that I'd forgotten one of the rules. That is always a key thing to consider, is there a rule you're forgetting? And to really double check that question, because your instinct is, of course, no. By this stage, I've obviously incorporated the rules into my mind, but that's not always true. Let's hope that actually is the final piece of the literal puzzle. We've got an 8, 9 down there, so that's a 5, 7, 8, 9, 5. Yeah, this should just solve itself now. That's a 6, that's a 5, that's not a 5, that's not a 6, that's a 6, 7, 8, 6, 7, 8, 9. I say this, but I'm once again, what am I missing? 6, 7, 7, 8. That's a 5, that's a 7, that's an 8, that's a 7, that's a 9, 7, 6, 8, 7, 9, 8, 6, 9, 3, 1, 9 and 8. Hey, no threes and corners. And how long did that take me? Well, for those playing along at home, just over an hour, I think. Well, a bit less than that with the description of the rules. I suspect strongly that I will have edited out a section of that puzzle where I was laboring for a long time over Sudoku before realizing that those two corner cells had to be the same. So experiment completed successfully. Make sure you can see this clearly. Black currant cells visited 44, black currants eaten 4, one-way doors used 0. The teleportation went exactly to plan. Although approaching it tentatively, Finks seemed to realize the importance of the moment. Molecular reassembly at the exit teleport was instantaneous and with near perfect fidelity, after which no change in cognitive function was detected. Experiment 7 will study Finks's performance when faced with a choice of teleports. Wow, it's such a cool idea. Having this sequence of puzzles. I mean, you can't do this without them being very well designed puzzles, and they are. So with that as the context, having a whole series of them that are related by this kind of fun narrative, and some quite creative rule sets as well. Like, although like there's creative language around the rule sets, they're also just, some of them are novel rules. Like this today, you know, having these teleports, either side of which has the same sum. You know, that's something he's kind of created for the purpose of this puzzle. I said 69 minutes there, but that's since I loaded the page, so it would have been about 55, I think. 26 solves, which is not that many actually. 2.5 days. Oh, I didn't. No, actually, it's only just been published, I think, not many hours ago, but I guess it was maybe test solved before that by a bunch of people. So like this puzzle, love this puzzle. Let's have a look at it in all of its glory. Yeah, beautiful conception. And as I say, it's a beautiful series. We're up to 6. He's just promised the 7th, and who knows where the end of the maze. Actually, it'd be quite interesting to see whether Marty comes up with a particularly fitting final episode, as it were. It's like writing a TV series, and that challenge of writing the final episode that satisfies everybody and that provides some sort of closure on the whole exercise. I have a sneaking feeling that even if the series ends soon, Finks will reappear from time to time in Marty Sears' catalogue. So thank you again to Marty, as always, for these amazing puzzles. Thank you to everyone else for watching and playing along. If you did, I hope you had success. I'll be back again with you, if not before, then Friday for the DA David Astle cryptic crossword, Australia's toughest cryptic setter. Until then, happy puzzling. I'll see you soon.